Hello everyone, today let's look at this method which is used in AP Calculus to approximate solutions. So you may recall that in the derivatives unit we have learned another way to the linear approximation. So for reference, the linear approximation is when you have a curve and then at x is equal to a, there is a slope of x of a, and then you use this to try to predict what the value will look for x. So this is like we have said the linear approximation, so it's just that the f of a slope is just roughly equal to L, which stands for linear approximation of x minus f of a over x minus a, and we can just rewrite this as L of x is equal to x minus a times f prime of a plus f of a. So in Calc BC, now that we know how to use differential equations, we can similarly find the solution of first order differential equations like numerically. So the formula in this case will be like f of a plus delta x is equal to f of a plus f prime of a delta x. So we find that it looks really similar to the linear approximation method, except that now we are using delta x. So instead of just directly approximating the value, we can use like different subintervals, so it's more accurate. So what does it mean? Like if I have a curve that looks like this, and I have a value here, and if I want to approximate this value, instead of just directly using a tangent line and trying to use this point to approximate this point, which wouldn't be very successful, we can just have a few subintervals where we each take different points and then try to use their tangent lines to find the value of the final solution, and that will be more accurate than linear approximation, especially if the interval is large. So of course, let's just do some practice so we have some hands-on experience using this method. So now we see that there is a y is a function, y is equal to f of x, and this is the solution to this differential equation with the initial condition f of 1 is equal to 0. And what's the approximation for f of 2 using this method with two steps of equal length at x equals to 1? So if we just have an arbitrary curve that looks like this with the y and x axis, if this is x is equal to 1, and we want to approximate f of 2, if there's two steps of equal length, then the steps should happen at 1.5. So each of the delta x is equal to 0.5. So now let's use the method. We can make a table so it's easier to keep track of. X is equal to 1, 1.5, and 2. So over here, y, as given by the initial condition, y is equal to 0 for this one. And dy over dx, which is just equal to 2x plus y. So we know that 2 times 1, which is x, plus y is 0, so it's 2. And now we can just find delta y, and delta y is, the change in y is just the slope times, so this is the slope times the interval, is equal to like dy over dx times delta x, and delta x is 0.5, so delta y is just 2 times 0.5, which is equal to 1. So we can approximate that when x is equal to 1.5, y is equal to 1. Now dy dx is going to be 2 times 1.5, 2x plus y, which is equal to 1, which is 4. So now delta y is just 4 times 0.5, which is equal to 2. So y used to be 1, and then this will be 3 because y plus delta y is the next y. So yeah, now we already have the coordinates when x is equal to 2, y is equal to 3, so the answer is D. So this method just tends to be algorithmic, and it can be a bit tedious if the amount of steps or like intervals are big enough. So that was it for today. Feel free to ask any questions in the comments if you have any, and we will be there to respond as soon as possible. Thank you.